Hey, hello and welcome to the introduction to software testing for chapter 7.1 and 7.2. Today we are going through a overview of the graph coverage criteria. Firstly, the graph coverage. Uh, our section today that we are going to learn is going to affect every part of the forest structure for modeling software. It is a very important part, and though seems very easy to understand, let's move on. First, the covering graphs. The graphs are commonly used for structure for testing, and it is extremely easy to make as well as understand with all the information you are going to need straight on the graph itself. The graph can come into from many sources as well. The control flow graphs, design structure, FSM and state charts, as well as use cases. And a test are used to cover the graph. Let's look at the definition of graph. Uh, the there are nodes as well as edges. We have a set of endnodes representing all the nodes that are in the graph, a set of NO of initial nodes, which the graph usually begins at, and final nodes, as well as the set of E for edges, which are connected from a node to another node. Let's look at some example graphs so you can visualize them easier. For the first graph, you can see there are four nodes from one counting from 1 to 4, with node 1 connecting to 1 to 2 to 3, and node 2 connecting to 4 as well as node 3. The node 1 is the initial node, representing with the arrow above its head, and the 4 is the final node, representing with the thick outline of the node itself. From At the bottom, you can see the information laid out very thoroughly, with the NO and F as well as the E representing it connects which node to which node. On the second graph, you can see a more complicated versions of a diamond node, but with a special loop at 2, 5, 9, and 6. And you can see the edges are not just starting from an initial node. It can move from the middle nodes to an additional nodes, or move from a final node to number 6 as the middle node. And finally, we have graph 3, but there's a special one. It doesn't actually have an initial node. So this graph is considered not valid. Let's move on. For the path, a path is a sequence of node. You can see from the previous graph, you can have a sequence of node as 1 to 4 or 1, 3, 4 for graph 1. That is called a path. The length of a path can be counted for the number of edges. A path have the amount of edges it has, that's the length of the path itself. Finally, the subpath. The subpath is a subsequence of nodes, and a P is a subpath of P. A subpath is a smaller part of path. For example, if you have a few paths like as follows of 1, 4, 8, and 1, 4 will be counted as a subpath of the bigger path 1, 4, 8. Next up is the test path and the single entry, single exit graph. Test path is a path that starts at a initial node and ends at a final node. The test path represent execution of test case for many tests and cannot be executed by any test at all. A single entry and single exit graph is have one initial node and one final node, as like this diamond graph right here, where you only have one initial node of 1 and one final node of 7. And there are and all the test path will starts with 1 and end with 7. Visiting and touring. Visit is a test path within a test path P visits node N, and if N is in P, as well as the edge. Tour is a test path P towards subpath Q, which means that you can tour a subpath within a bigger path. You can look at the example right down below. For the we can also have the path definitions. We have path small t, which is the test path executed by test t, and a test path big T is a set of test paths executed by the set of test t. Each test can be executed one and only one test path. The complete execution from start node to a final node. A location in a graph can be reached from another location if there is a sequence of edges from the first location to the second. Let's move on to the next slide. We can have a many-to-one test or a many-to-many test to test path. And we usually use graph as a developed model for the software as a graph, because graph are easy to look at and easier to understand, and we can see every flow and data that is within a graph better than just looking straight at the codes. As well as we can visit or tour specific set of nodes and edges as we like and as much as we like, due to the fact that it is easy to perform. A test requirement, we usually call them TR, and describe properties of a test path, as well as the we have the definition for test criterion and satisfaction. Let's talk about coverages. We have a few coverages to talk about, so let's start with node and edge. The first is the node coverage. Well, obviously this is the very, very complicated definition, so we are going to reduce to the second one, which is the test requirements contains each reachable node in the graph. For example, if you have a graph of 1 to 4 that has 1, 2, 3, and 4, the node coverage would covers all the nodes, which is 1, 2, 3, and 4. We write them out. Next up is the edge coverage. For the edge coverage, a test requirement contains each reachable path of length up to 1 and inclusive, which they are non-repeat. For example, if you have, like I said, a graph of 1, 2, 3, and 4, the edges that that connects the nodes that are predetermined will be a part of edge coverage. And next is the path with a length of 1 and 0. For example, a graph with only one node will not have any edges. Seems trivial, but edge coverage needs to require node coverage for this specific graph. What about covering multiple edges? Well, we have edge pair coverage. Edge pair coverage requires a pair of edge or a subpath of 2. For example, if you have this graph right here, A edge pair coverage would be a, a pair of two edge. For example, you have 1, 4, and 5, 1 to 4 and 4 to 5. An edge pair coverage would be a 1, 4, 5 that covers two edges. That is a part of edge coverage. Next up is the complete path coverage, or for short CPC. The test requirements contains all paths in G. Unfortunately, this is impossible if the graph has a loop. And next up is the specified path coverage, or SPC, which the test coverage contains a set of S of test path, where S is supplied as a parameter. So let's look at an example for node coverage and edge coverage that we have just learned from before on this graph right here. We can see a node coverage of 1, 2, 3, 4, 5, 6, and 7 with two test paths. We also have the edge coverage that shows all the edges, and the edge pair coverage, as well as the complete path coverage.